Okay, we're diving into a really cool problem today. Imagine you've built something that runs unbelievably fast. How in the world do you watch it, how do you monitor it, without completely wrecking its performance? It's this constant battle between speed and just knowing what's going on. Let's get into it.
So, let's just start with a quick thought experiment. Picture your program. It's doing its thing 1.6 million times, every single second. So, is that good? I mean, is that fast or is it actually kind of slow? It feels like a huge number, right? But the truth is, without more information, that number is basically useless.
And that right there is the core of this whole performance puzzle. A number like 1.6 million operations a second sounds impressive, but it can be super misleading. It could be world-class, or it could be horribly inefficient. So what's the missing piece of the puzzle here?
Well, it all comes down to the hardware. That's the secret ingredient. The exact same code can give you completely different results depending on what it's running on. Is it a basic CPU, a specialized chip, a monster of a graphics card? That changes everything.
So let's dig into that relationship a little more. This dance between the hardware, the software, and the raw speed you can get. The source material we're looking at gives us a perfect, and I mean perfect, example of just how massive the performance gap can get.
And boom, here's the answer to our puzzle. Remember that 1.6 million operations per second? Turns out that's our baseline on a standard CPU running pure software. Kind of pokey, actually. Now, run that same task on a CPU that has hardware acceleration, it jumps to 614 million. And on a powerful GPU, we're talking 2.18 times billion operations a second. That is a completely different universe of speed.
And that leads us to a really important idea, the high-frequency operation. Think of something small and efficient, like AES encryption. It's a cheap, simple task that modern hardware is literally built to do at insane speeds. But this incredible power creates a brand new and very tricky problem.
And yep, that problem is what we're calling the logging dilemma. See, you need to watch your systems. You have to log what they're doing to make sure everything is working right, to check for errors, all that good stuff. But how do you log something that's happening a billion times a second?
Let's make this real. Think about that hardware-accelerated CPU cranking out over 600 million operations every second. If you try to write a log entry for every single one of those, well, the logging itself becomes the bottleneck. You've hit the brakes on your super-fast system just by trying to look at it. You're destroying the very performance you're trying to measure. The source material really puts it bluntly. When you're dealing with these high-frequency systems, trying to log anything more than the absolute bare-bones minimum will tank throughput. Your rocket ship of a process just grinds to a halt.
So, how do we get out of this mess? Well, the trick is to realize that not all operations are the same. And to really see what I mean, let's look at a classic matchup in the world of crypto, AES versus RSA. They're like polar opposites when it comes to performance, which makes them the perfect case study for why you need totally different monitoring plans.
First up, we have AES. Like we saw before, on a modern CPU with the right hardware support, you can just churn through over 614 million of these every second. It's the poster child for a high-frequency, super cheap task.
And now, look at RSA. Even if you throw a 20-core beast of a system at it, you could only manage about 77 operations a second. 77. That's it. It's complex, it's slow, it's computationally expensive. It's the total opposite. A low-frequency, very high-cost operation.
And this just lays it all out, doesn't it? We're talking about two completely different worlds. On one hand, you have AES, high frequency, cheap to run. So your logging strategy has to be, well, skimpy. On the other hand, you have RSA, low frequency, super expensive. With that, you can afford to have rich, detailed logs for every single operation. It's all about matching the logging to the workload.
So what does this skimpy strategy actually look like for those super fast systems? The source material has a great name for it, the Skimpy Contract. Think of it like a deal you make with your system. You promise, I will only log the absolute most critical information, and in return, you'll keep running at full speed.
Yeah, the whole goal of this contract isn't to capture every little detail. Instead, what you're trying to create is what the source calls a cryptographic heartbeat. It's like you're not putting the system through a full-body MRI scan every second. You're just checking its pulse every now and then to make sure it's still alive and healthy.
So, what actually makes the cut? What do you keep? Well, first, a final validation block. That's just a secure summary right at the very end of the process. Second, you log a single signature the exact moment you find a match, or you get the result you were looking for. And third, you log a tiny periodic signature, that's our heartbeat, every so often, say every 32 batches of work, just to confirm things are still running smoothly.
But you know what's even more important? The skip list. This is the stuff you absolutely, positively do not log. We're talking no raw data dumps, no big matrices for visualization, and definitely no digging into the internal state of the AES operations. This is the heavy stuff that creates huge logs and just murders your throughput.
So why is this Skimpy contract so effective? It really comes down to three things. First, you get integrity. Those little signatures are a rock-solid cryptographic guarantee that nobody's messed with the process. Second, performance. The overhead is so tiny it's basically zero, so your speed is protected. And third, safety. You're not logging any sensitive bulk data, which keeps your logs small, manageable, and secure.
When you boil it all down, the key takeaway is this golden rule. You have to match your logging richness to the operational frequency. If your system is running incredibly fast, you keep the logging skimpy. If it's slow and deliberate, you can afford to get rich and detailed. It's such a simple idea, but it solves a really, really complex problem.
And that leaves us with one last, kind of mind-bending thought. Today, we think of an RSA operation as slow, something that deserves a rich, detailed log. But as computers keep getting exponentially faster, what happens then? How long before today's complex, rich operations become tomorrow's high-frequency tasks? What kind of skimpy contract will we need when we're trying to monitor 1 trillion operations per second?